Okay, good morning, class. Um, as promised, I wanted to give you a recording of a more challenging problem from topic 4 about Newton's laws of motion. And because last time we didn't touch very heavily on the tension force, I thought we'd do a problem like that, okay? So I've already worked this problem, but I'm going to show you the various steps that I would use to solve this. Okay, this is very similar to a problem that's found in the reading in topic 4. So if you need like another example, you can go reference that and you'll find one very similar to this one. This is actually from your homework as well. So when you do this assignment in your homework, make sure you consult kind of this strategy, and that way you'll be able to get that assignment done pretty quickly. Okay, so this question says, calculate the tension in a horizontal strand of spider web. If a spider of mass 8 times 10 to the minus 5 kilograms sits motionless in the middle of it, much like the tightrope walker in figure 1. The strand sags at an angle of 12 degrees below the horizontal. Okay, so in this drawing they gave us, this isn't actually the problem that they want us to solve. This is just an example to help us understand the problem we want to solve. We can see if an object is being weighted onto a string that's supported by 2 posts on either side, you'll see that there's 3 vectors that we're interested in. There's the weight vector that's pulling down on the man with, that's his gravitational force. There's a tension force that's being pulled up and to the left by the left post, and there's a tension force that's pulling up and to the right by the right post. Okay, so those are the 3 forces we need to worry about. So to find the tension in each rope, there's a couple things we need to do first. Okay, so I've numbered these steps next to the boxes that I'm going to reveal them in. So first thing that I would do is I would draw a picture to represent our situation. Okay, so how I chose to do it, you can see I've set it up very much like the drawing on the left. I've drawn a free body diagram, except I've substituted the angles with 12 degrees, like the problem said. I also made a point to draw some axes, just so, because I know that some of you struggle with direction and how to represent that on a free body diagram. Here's my x-axis, here's my y-axis. I drew them in dotted lines so that you wouldn't get confused with the vectors that are drawn over them. Okay, but remember that anytime we go along a positive x-axis, we're talking about positive values. So I put a little plus sign there to remind you of that. Anything that's along the negative x-axis, try to make those just negative values. Okay, same with the y-axis. If you're going up the y-axis, make those positive values. If you're going down the y-axis, make those negative y values. Okay, but you can see that it's drawn very similar to the tightrope walker on the left-hand side of your screen. Okay, so that's the first step. Really just draw the situation. Step 2, what I did, I figured, well, they already gave me how much he weighs. He weighs, or the spider weighs 8 times 10 to the minus 5 kilograms. Okay, so right then and there, a very easy thing we could do first is figure out the gravitational force by timesing his mass times negative 9.8. Okay, remember that equation, W equals mg. So if I times 8 times 10 to the minus 5 by negative 9.8, I get that his gravitational force, his weight, is negative 0.000784 newtons. Okay, now we're not going to use that number right now, but we're going to shelve it. We're going to come back to it later. Okay, next, the next thing I did, I started looking at each of these tension forces in an x direction first and a y direction next. Okay, so remember that it's always important whenever you're dealing with diagonal forces like the ones we're dealing with in our drawing right here, these 12-degree forces. It's always a good idea to take each of those diagonal forces and make them into a triangle. Okay, so we know that this diagonal force is headed this way, It's 12 degrees, okay? So whenever we have a diagonal force, we could always talk about its horizontal aspect, which we could call x. We could talk about its vertical aspect, which we could call y. So I'm going to be showing you my horizontal work here on the left, and then we're going to switch over to the vertical work here on the right. Okay, so just to give you some context. So my next thing I did, in my x column for my work, since I'm working on horizontal stuff first, I made the observation that, hey, this spider is not really moving at all right now. The spider is just sitting there on this strand of web. So there is no horizontal motion that's actually going on right now. He's just sitting there. Okay, so I can make the assumption then that my tension force in the x direction is 0, since there's no movement in the x direction in either direction, to the left or to the right. So I could say that, hey, my T sub net x is 0. Now remember, T sub net is just a fancy way of saying total force in the x direction. Okay, so because he's not moving, T net sub x is 0. So I could say, okay, well, my tension on the right side in the x direction, okay, so in other words, my tension on the right side would be this guy right here. It's the x aspect of the arrow that's going off diagonally to the right. That value, whatever it is, and I don't know what it is yet, if I subtracted the tension in the x direction on the left side, so if I drew like another triangle, kind of like this, you'll notice these two triangles are going to be congruent to each other. Okay, so it makes sense that if I take the right side, which is positive, since it's going up and to the right, if I take away the tension in the left rope in the x direction, which is this guy right here, and since that's going off to the left, that's going to be a negative value. So TRX minus TLX should be 0 because they're equal to each other. These are congruent triangles after all. Okay. Therefore, if I added that TLX over to the other side, I've now proven that the horizontal components of my left and right tension forces are equal. So these are equal to each other. That's all we're saying. And that's not too hard to understand because we have the same angle on either side. Okay. So now let's talk about the trig that's involved in this problem. So here's kind of another drawing. I've tried to draw these as simple triangles. And remember that whenever you're doing these vector problems, you need to be very conscious of things you learned back in geometry class. So I've got SOHCAHTOA, which is this acronym for sine, cosine, and tangent. So sine is equal to opposite over hypotenuse, cosine is equal to adjacent over hypotenuse, tangent is equal to opposite over adjacent. Hopefully you learned that back in geometry. But let's suppose that I wanted to figure out expressions for TLX and TRX. Okay, so let's deal with the left triangle first. Okay, so I've got 12 degrees. And oops, I think I put 5 in here because I was getting mixed up with the tightrope problem. Let me substitute this in, and that might change my answer. Who knows? It should be 12. Sorry about that. Okay, so if you look at the triangle, TLX, this triangle on the right, so this right here, if I wanted to figure out TLX, you see how TLX is the adjacent side to that 12 degree? If that's the adjacent side, I could use the cosine function to solve for it. So since cosine is adjacent over hypotenuse, I could say, hey, cosine of 12 degrees is equal to TLX over TL, because TLX is my adjacent side and TL is my hypotenuse. Okay, so that's kind of how we're setting this up. Now, if I go further with this, and let's say I tried to get TLX by itself, all I would need to do is times that TL to the other side. Okay, so now I know that TL times the cosine of, once again, that should be 12 degrees. Okay, let me fix that. 12 degrees should be equal to TLX. All right? Okay, so let's do the same thing to the other side. So if I was talking about the right triangle in my little drawing up above, it's the same process. If I wanted to figure out what TRX was, I could simply set up the cosine ratio again. Okay, so cosine of 12 degrees, since it's the same triangle, just opposite, is equal to its adjacent side, which is TRX, over its hypotenuse, which is TR. Okay? So if I get TRX by itself, just like we did with TLX up above, I find out that TR times the cosine of 5 degrees is equal to TRX. Okay, now we're dealing with a lot of variables here. Okay, so just to remind you, TRX and TLX are just the x components of these two string forces that are holding the spider up. TR and TL are just the total tension in the rope. Okay? And remember, this problem is asking us for the tension. So we're trying to get the total tension on either side. Okay? So TL and TR are really what we're interested in at the end of the day. So we're kind of moving towards those. Okay, let's go back to what we said here in the middle. We said that TRX should be equal to TLX. Well, look at us. We have equations that are solved for TLX as well as for TRX. So let's go ahead and do some substitution. So if I take those two equations that I just got for TLX and TRX, and I substitute them into the equations over here in the middle, I know that, so what I did was I took this equation, plugged it in for TLX. I took this equation, plugged it in for TRX, just in case you're lost, okay? So when I do that, we get that TR times the cosine of, once again, it should be 12 degrees. Sorry, guys, 12, not 5. 12. 12. Once again, I should have been looking at the spider problem. I got confused with the tightrope. And that should be 12 as well. But all I'm saying is, if you substitute those expressions in over here where we did our middle work, we get TR times the cosine of 12 degrees is equal to TL times the cosine of 12 degrees. You'll notice that when we're timesing by the same thing on both sides, we can just cancel. Okay? And so we then come up with a conclusion. TR should be equal to TL. And once again, this isn't really that complicated because the triangles are congruent, right? These triangles up here are congruent. So it really makes sense that TL and TR, the total force coming from each string, would be the same. Okay, so since TR and TL are the same, let's just call them T. Just to kind of, you know, wrap up this conclusion that they are the same. We'll just call them T. Okay, so our horizontal work is done. We've already got an equation for T. Okay, let's do the vertical work now. So I'm going to start out with the same assumption I start out with the left. Because there's no vertical motion in this problem, the spider's not actively moving either up or down right now, I know that the total force in any vertical direction is going to be 0. So if I take a look at my two triangles that I drew up here, my vertical aspects of either are these two y's right here. If I take TLY, which is the y direction here on the left side, and if I add it to TRY, which is the y component on this triangle, and if I add that with his gravity, with the spider's gravity, which is W, now remember I'm making W negative because gravity always pulls down, but if I add those three forces together, I should get 0 because there's no movement right now. Okay? So I can do this similar thing to what I did on the other side of the problem. Let's set up our triangles. This time, instead of using cosine, we're going to use the sine, because the sine function, remember from SOHCAHTOA, sine is opposite over hypotenuse. If I go to my triangles, and if I go opposite them, okay, I'm going to get my y component, okay? So I could say, okay, the sine of, once again, 12 degrees is equal to my opposite side, which is TLY, okay? We're talking about this left triangle first, right here. So TLY divided by its hypotenuse, which we're going to call TL, okay? Very similar to what we did on the horizontal side of our work. Okay, and if I times that TL over, I now know that TL times the sine of 12 degrees is going to be equal to TLY. On the right side, we do the same thing. The sine of 12 degrees is equal to its opposite side, which is TRY, divided by its hypotenuse, which is TR. I'm going to multiply that hypotenuse over, and we get TR times the sine of 12 degrees is equal to TRY. Okay? A lot of repetition in this problem, but I hope that the concepts themselves are making sense based on what you learned in geometry class. Okay? Now we get to kind of our final step where we're wrapping everything up. Because we know that our y forces have to add to be 0, let's go ahead and plug these in. So, because I have expressions for TLY and TRY, okay, I'm going to plug these in to the equation I was dealing with up here, where I said they have to sum to be 0. Okay, so I'm plugging these expressions in there. Okay, I'm going to go ahead and plug in my weight, since we already figured that out at the very beginning of the problem. And so we get this expression that says TL times the sine of, once again, 12 degrees, silly me, plus TR times the sine of 12 degrees, minus 0.00784, and I think that should be an extra 0. Come up here. The sum of those three forces should equal 0. Okay. Now we've got two variables in this equation. Okay, so something's up here. But remember that over on the left-hand side, didn't we say that TR and TL are the same as each other? Which I just decided to call them T since they're the same. I could just call them anything I want to. So now you'll notice that I'm substituting in just plain old T into those, into that equation. Yeah, once again, there should be an extra 0 here. It should be 12 degrees, 12 degrees. Okay. So I'm just substituting in to make this simpler. Now I'm only in one variable, guys, which whenever we have one variable in algebra, we can get one variable by itself just by moving things around. So I have t times the sine of 12 degrees plus t times the sine of 12 degrees minus 0.000784 should equal 0. Okay, now let's do some combining of like terms. Because I've got two of these terms that are t sine of 12, I can just combine them and put a 2 in front as a coefficient. Okay. Once again, it should be 12. Gosh, that's annoying. Okay, so 2 sine of 12 degrees minus 0.000784, which is his weight, should give us 0. And now we just got to get t by itself. So first thing you got to do is plus that 0.000784 over the other side. Okay, which means that 2 times the sine of 12 degrees should give us 0.000784. Okay, and then I'm going to divide the 2 over to get the sine of 12 degrees should equal whatever 0.000784 divided by 2 was. And it looks like I already, when I did this for you last night, looks like at this point I times the 2 and the sine of 12 degrees together, okay, to get a value that I could put in front of t and then divide over. But because I got mixed up with the tightrope blocker and the spider, I need to change that to 12. So if I take 2, and if I times it by the sine of 12, okay, I'm going to get something different. So let me do that for you right now. So I'm on my calculator right now. 2 times 12 sine equals. So what I should have gotten was, let me just double check my work here, 12 times 12 sine times 2. Yep, that's right. I get 0.416 is what I should have gotten there, since I made the mistake of using 5 instead of 12 degrees. So 0.416 T should be equal to 0.000784. Okay, and then very last step, I got to divide that 0.416 over to get T alone. Okay, so 0.000784 divided by 0.416, and I've got my tension force, T. Okay, and since I'm kind of running out of room here, I'm gonna write my final answer over here on the left-hand bottom side of the screen. So T should be equal to 0.00188 newtons. Okay, that is our final answer. Now, these problems can be very daunting. So just to let you know, I've gone into your homeworks and tried to remove as many of these angle problems as I can, just to kind of lighten your guys' load a little bit. But there may be a couple in there because I want you at least to practice this trigonometry. So just to kind of do a quick summary of everything we did. Step 1, we drew a picture. Okay, we got ourselves oriented with our directions. Step 2, I went ahead and just easily figured out what the guy's weight was, since that was what the spider's weight was, rather, since that was gonna come up later in the problem anyway. Step 3, I then started considering the spider's horizontal components of those 2 rope forces. Okay. Step 4, I started resolving those rope forces into horizontal components. Okay. They were only equations that I resolved them into, but I would use those equations later. Step 5, I then realized that the right and left components of those 2 ropes were the same, which meant that total tension in both of those ropes was the same. Okay, so I just found a way to relate it to just one simple variable. Step 6, I went over here to the vertical side of things, and I made the same assumptions. So I said that through the 3 vertical forces, the 2 components and his weight would add be 0 because there's no movement going on in the vertical direction. Then I did the same thing with the trigonometry. I resolved those 2 rope forces into their vertical components using the sine function. Okay, and then I came to the same conclusion, really. So then I plugged in those trigonometric expressions into my vertical motion equation I wrote up here, and then I just started combining like terms and solving until I got what tension was, which is 0.00188 newtons. I hope this helps. If you want another example, or if you wanted to maybe chat with me on a one-on-one basis if you'd like, email me. We can set something up where we can do another example with you and get you guys used to this, okay? But there you have it, a tension and force example that's a little bit more complicated. Hope you enjoyed this recording. Please watch it, and I'll see you guys in our next class.